Hello everybody, welcome to my 40-second video. This is on GF4 sum and product gates. I'll be going through the functions or how to build the functions in my 41st video, a Quaternary Reed Muller Algebra. So these are how you build the gates for algebra. Okay, so first we're going to start off with the GF4 sum gate. Here I've got A, B and A plus B listed as before, in the previous video. A1, A2 for A, B1, B2 for B, and A plus B1 and A plus B2 for A plus B. Now they're all coded according to this truth table. So if x equals 0, 1, 2, 3, x1 equals 0, 1, 0, 1, and x2 equals 0, 0, 1, 1. This is straight quaternary to binary conversion, so I'll be using this throughout. Okay, so yeah, as I've said, A plus B is coded according to this. A is A1 and A2 according to this truth table, and B2 and B1 is coded according to this truth table. So right. Here we have the counter maps for the sum gate. This is A plus B2 here. This loop here is A2 and not B2. And this loop here is A2 and B2. So A plus B2 equals A2 and not B2, or not A2 and B2. And this is the definition of the exclusive OR gate. So saying that A plus B2 is equal to A2 exclusive OR B2, and if you complement both the inputs of an exclusive OR gate, it performs the same function. So this is equal to not A2 exclusive OR not B2. Just means I can get away with using one hex Schmidt trigger per input instead of two. So this is A plus B1. This is a counter map for A plus B1. This loop here is not A1 and B1, and this loop here is A1 and not B1. So A plus B1 equals A1 and not B1, or not A1 and B1, which again is the definition of the exclusive OR gate. So A plus B1 equals A1 exclusive OR B1. And as before, in this example, I've complemented both the inputs, so I can just use one Schmidt trigger instead of two. So A plus B1 equals not A1 exclusive OR not B1. This is a circuit diagram for the sum gate, GF4 sum gate. Here we're using quaternary to binary conversion here. If you don't understand how this works, I've got a video on it called quaternary to binary conversion. I think it's my 37th video or something like that. Anyway, so this is A, this is A2, and this is not A2 and not A1. This is input B, this is not B2 and not B1. And these are exclusive OR gates here. And you convert the binary into quaternary by these two resistors here. This is a 200 ohm resistor, this is a 390 ohm resistor. And this is the output, A plus B, GF4. GF stands for Galois field, by the way, and 4 refers to the base. Here we have the GF4 product gate. Again, quaternary to binary conversion here. Listed A, B and A times B. This is B2 and B1 for B, A2 and A1 for A, and A times B2 and A times B1 for A times B. So they're all coded according to this truth table here, as with the sum gate. So let's have a look at the circuit counter maps. These are the counter maps for the product gate. This is A plus A times B2. Right. there's 3 loops going on here. This is A2 and B1 here. This loop here is A1 and B2, and this loop here is A2 and B2. Now I'm connecting them together with the exclusive OR gate instead of the OR gate. This is Quaternary Reed Muller Algebra. So the rule is, if you loop a digit an odd number of times, it's a 1, and if it's an even number of times, it's a 0. So these ones are looped once. This one here is looped 3 times, and this loop here is looped once. These zeros are both looped twice, so the 0. 0 loops being even, so any unlooped coordinates are 0. So we have A times B2 is A1 and B2, exclusive of A2 and B1, exclusive of A2 and B2. Now I'm using De Morgan's theorem here to convert these ANDs into a NOR. It just means I can invert the inputs and use 1 switch trigger per gate instead of 2. So yeah, it's just De Morgan's theorem to convert the AND into NOR. So A times B2 equals not A1, no, not B2, exclusive OR, not A2, not NOR, not B1, exclusive OR, not A2, exclusive or NOR, not B2. So for A times B1 kind of map, we've got 2 loops going in here. Same rule again, if the coordinate is looped once, it's a logic 1. If looped twice, it's a 0, logic 0. So these are looped once here, these are 1s. This coordinate here is looped twice, so it's a 0. And of course any unlooped coordinates are even, so 0 is even, so it's a 0. So we have A times B1 equals A1 and B1 exclusive OR A2 and B2. I'm using exclusive OR instead of OR. And again, I've used De Morgan's theorem to transfer the AND into a NOR. Just as before, it means I can only just use 1 Schmidt trigger per input instead of 2. So A times B1 equals not A1, no, not B1, exclusive OR, not A2, no, not B2. This is the product gate circuit diagram. Again, quaternary to binary conversion going in here. Got inputs A and B here. A2 and not A2 and not A1 for A, and not B2 and not B1 for B. These are the NOR gates from the kind of maps in the previous page. This is an exclusive OR gate. I'm using this not A2 and not A2 and not B2 twice here, so they're feeding into both inputs here. These are exclusive OR gates. This is equivalent to a 3 input exclusive OR gate. So all these gates here are summed together with the exclusive OR gate. And again, the output resistors, 200 ohm and 390 ohm resistor, to turn the binary into quaternary. So this is the 8 times gate GF4. So we're going to have a look at the union operators. I think I can just squeeze that in. Yeah. So the squared gate is A times A. So 1 times 1 is 1, 2 times 2 is 3, and 3 times 3 is 2, according to the product function truth table. Here we have, again, quaternary to binary conversion. A equals 0, 1, 2, 3, A1 equals 0, 1, 0, 1, and A2 equals 0, 0, 1, 1. And here we have the output A squared, and this is A squared 2 and A squared 1. So A squared is a 0, so it's 0, 0. A squared is a 1, so it's 0, 1. A squared is a 3, so it's 1, 1. And A is a 2, so it's 1, 0. So A squared 2 is A2, that's similar to A2. and A squared 1 is A1 exclusive or A2 here. And for the same reasons you can complement both the inputs, and with the exclusive OR gate, and it performs the same function. So A squared 1 equals not A1 exclusive or not A2. So this is the A squared gate circuit diagram. Here again, binary, quaternary to binary conversion. This is output not A2 and this is output not A1. So it's inverted there to give an A2 output. This is not A squared 2 equals A2. This would be not A squared 2 output, and not A squared 1 output is A1, not A1 exclusive or not A2. This is exclusive OR gate. So this would be A squared 1, that output, and again converting the binary into quaternary. You've got a 200 ohm resistor there, and a 300 ohm resistor there, 390 ohm resistor there, and this is the output A squared. Right, this is the cube gate of A0, 1, 2, 3, and A cubed, which is A times A times A, or A times A squared if you like. It doesn't matter how you do it. So A cubed is 0, 1, 1, 1 in response to A 0, 1, 2, 3. Now I haven't drawn any, I've just gone to the circuit diagram, I haven't drawn any truth tables or anything. This is, if this input A is the quaternary input, if it's a logic 0, the output will be a 0, and if it's above logic 1, quaternary logic 1, 1, 2 or 3, the output will be a 1. This will switch to 5 volts when A is above as a quaternary logic 0, and the resistors knock it down to a quaternary logic 1 voltage. So this is a 390 ohm resistor and this is a 200 ohm resistor. So that's the output A cubed. Right, I think that concludes the video. Just like to say, hope you enjoyed it. Thanks for watching. Bye.